Hello, this is Team 3 from ECE 4534. My name is Dave Lockhan. I was in charge of the flag capture rover.
My name is Morgan Dykeshorn, and I was in charge of the sensor rover.
My name is Cameron Helster, and I was in charge of the Tagger rover. This semester's ECE 4534 project was capture the flag using autonomous rovers that communicated via Wi-Fi. Our team had 3 members, thus we implemented 3 rovers: the sensor rover, the flag rover, and the tag rover. The sensor rover was responsible for using a variety of sensors to scan the map and convert sensor readings into obstacle and rover data. The flag rover's responsibility was to traverse both sides of the map, our side and the enemy's side, and capture the flag that was in the enemy's defense zone and take it out of the flag zone. The tag rover's responsibility was to tag the enemy rover once it reached the defense zone to ensure that it could not reach the ally flag zone and capture the enemy flag.
This is the flag capture system that we created. To start, this is our flag, and it's about 2 inches by 2 inches and 6 inches tall. And the reason we made it that tall is so that the sensor rover would be able to detect it. On top of the flag, we have a magnet, and the basic idea is once the rover reaches the flag, it will drive over it and pick it up with the metal disc. There's a sensor on top here, which is the Hall effect sensor, and that will detect a change in the magnetic field. And once that's confirmed that we have indeed captured the flag, we'll use the line array to find tape. And now that we know we're outside the zone, we'll use the servo to drop the flag like so.
So the tagger uses 2 main sensors: the reflectance array sensor that the other 2 rovers have, and 2 mechanical bumpers to detect tags. Now, all that happens with the mechanical bumpers is once the metal wire hits the nut right here, it closes the circuit and sends a low voltage from the original high voltage to a GPIO pin that is connected to the bumper.
The sensor rover utilizes 3 main sensors. First, the time of flight sensor mounted above the 3-inch obstacle mark helps detect rovers. Next, the ultrasonic sensor, which emits ultrasonic sound waves to detect obstacles, is mounted down lower. There are 2 IR sensors also mounted on the sensor tree, but the data from these sensors proved to be unreliable during operation. Lastly, there's an IR reflectance array mounted on the front and back. These arrays help the rover detect tape and follow blue tape lines. Lastly, the ultrasonic sensor and time of flight sensor are mounted on a servo, which allows 180 degrees of rotation, which is useful in detecting obstacles and rovers. For the sensor rover map generation, we start with an occupancy grid that has 8-bit values in each cell. Our grid on the rover was 84 by 60 inches, which represents the maximum size arena possible. This is an example of a small section of that map, where each cell contains a value of 255. A value of 255 represents an obstacle being in that cell. A value of 0 represents no obstacle. Now we detect obstacles using the ultrasonic sensor, which emits a cone-shaped beam, such as this. As we scan through the arena, we overlay a cone on cells, which subtracts obstacles, which subtracts a certain probability of there not being an obstacle in that cell. So every time a cone gets overlaid on a cell, it subtracts 20. And as we go across, it keeps decrementing cells. When we get to an obstacle, the cone obviously shifts down, so less cells get decremented from. And then it keeps going across and keeps scanning. After complete scan, our occupancy grid would have values similar to what's shown here, with 0 representing no obstacle and 255 representing an obstacle. This was where the obstacle was while I was showing that scan. Now, we obviously can't send out 5,000 different obstacles to the other rovers. It would overload the network and be an unreasonable time to send those obstacles out. So instead, we implement a technique called template matching to find where the obstacle is on this grid and only send it out. To do this, we overlay templates that represent an obstacle that we try to match to every square of the occupancy grid. This template basically sums the values of the occupancy grid. In this case, it was all zeros and 255 compared to values of all 255, and checks the difference. And for it to be a match, the difference has to be less than 80. In this case, you can see that the difference is going to be well over 80, so it doesn't declare it a match. It keeps checking for every possible location that this template could go in the entire grid. In this case, there is no match for a 3x3 template. So then it goes down to the next smallest size, which is a 2x2 template, and tries to match it in every grid of the arena. The first reasonable match that it's going to find is this match here, which is all 255s in the occupancy grid, and obviously the template is also 255. So it sets it as a match, and then goes on and tries to find more matches. Because the smallest obstacle size was 2" by 2". A 2x2 template is our smallest size, so it would not find this as an obstacle as well, due to not having a 1" template to match it with. After the templates are matched, we have a list of containing between 100 to 300 different obstacles that are sent out to the other rovers in individual JSON messages. Each JSON message contains the bottom left corner of the object, which is the template, and then the length and width of the templates. Our templates range from 2 inches to 10 inches to knock out large areas of the arena.
One thing that was required for the rovers to traverse a map without hitting any obstacles was a good pathfinding algorithm. The pathfinding algorithm we decided to use was the A-star algorithm, a simple but effective lowest cost path algorithm. The way A-star works is it uses a map of grid points, or cells in our case, to decide where to traverse. The cells that we had 3 significant values: G-score, H-score, and obstacle value. The way A-star works is it receives a start node and a goal node and goes through the entire map setting the G-scores and F-scores of every cell based on the start and goal node. The G-score for a cell represents the distance from it to a whatever neighboring node put it into the list of nodes to look at, while the H-score is the actual physical distance from a certain node to the goal node. Once the entire traversal is finished, the goal node will be connected to the lowest cost path. Now, the obstacle value solely represents a cell that the rover itself, whether it be the tagger rover or the flagger rover, the rover itself cannot exist there, whether that is an obstacle itself or the rover would intersect an obstacle at that point.
In order to control rover movement, we had to do a few things. The first was to be able to create a PI controller, which is a proportion and an integral controller, which allows the rover to go straight or to make accurate turns. So basically what happens is inside of the motor there's an encoder, and so we get the number of ticks per revolution based on this encoder value. And then we run an algorithm that allows it to correct for itself, because the left and the right motor aren't always going to be the same values. And this algorithm allows us to make sure that the rover is able to automatically correct itself, so that way it can go in a straight line or make an accurate turn. We did a lot of data recording to see how many ticks exactly it would require for the rover to move a certain amount of distance or to make a certain degree turn. This data was then taken to be able to make the rover go a certain distance or traverse along a path. Based on the movement that we get, we are able to track the position of our rover. So after we send it its initial position, based on the encoder ticks readings, we know whether it's traveled 1 inch or 2 inches, and this allows us to keep a precise track of where the rover is going and what orientation it thinks it's at. In terms of communication, we had this network adapter which plugged into our computer, and that ran the server and any of the clients that we had on our computer. We had a Wi-Fi that would go on the rovers, and this would connect to the network adapters. All the communication that happened from the Wi-Fi to the server, and then the server would relay out the messages to the other Wi-Fis and other clients connected to the server. In terms of the message format, we used specific start and stop bytes, and had a specific checksum which allowed us to know whether we are dropping or conveying an incorrect message. The content of the message itself was contained inside of a JSON payload, and that is the method that we use to transfer all the data from the rovers to the server. Yeah. We spent a good amount of time on the communication between the rovers and the server in order to make sure that we establish a reliable connection, so that way that was not something that we would have to fix going on in the future. One of the limitations of our project has to do with the battery. And if the battery is low for, let's say, the flag capture rover, then it's not able to detect and capture the flag once it's inside the flag zone, because the Pixie Cam requires enough power that if the battery is low, then it'll affect the readings.
Another sensor that is affected by battery power are the IR reflectance sensors. These sensors work by emitting an IR light and then detecting the reflectance of that light. However, if the battery is low, it can't emit as much light, therefore less is reflected, and it affects our readings that are set based on thresholds. Other sensors on the sensor rover are also affected by power. There are a lot of fluctuations in the ultrasonic readings when a lot of power was used by the servo motor, which was mainly remedied by putting it on a separate power wire to the battery.
In terms of the rovers running together, we can guarantee that the rovers can run together for an extended period of time. However, there are certain aspects that make the rovers unable to move or perform their specific functions during certain runs, such as the sensor rover sending obstacle data that makes a particular rover believe that is within an obstacle, making it completely unable to find a path. Other times, the sensor rover sending rover data that isn't completely accurate, making something like the tagger rover, which moves toward any rover that isn't itself, or the flag rover, move towards a rover that isn't necessarily the enemy and may be just bad rover data that the sensor has sent.
Another limitation of the project is the server parsing. When we parse the JSON messages that are coming in, we often found that the obstacle data would be dropped because we're sending the obstacle data at such a fast rate. One of the ways we fix this is by slowing down the rate at which we are sending the obstacle data from the sensor rover to the other rovers, but we still found that there were times when the server would drop obstacles over the network. One of the things that we did not meet the requirements for is the ability for the sensor rover to initialize and orient all of the rovers. We had a tough time in getting the magnetometer and the compass to work on our rover, and when we had implemented the initialization without the sensor rover, we were relying on too accurate of data, which was not feasible when we were in the integration phase.
Another change that the sensor rover could have made to make data better and to have better maps is, instead of having a rotating sensor tree, just have multiple of the same sensors at different angles. These fixed angles would be less prone to error when reading them and allow for a better map to be made than just a single sensor that would pass at one angle, or even the rotating sensor due to the less error in the movement.